Next one up is Roman Jaresch from Work Microwave. And the presentation is entitled QV and Wideband Demonstration.
So thank you very much for the invitation, which I appreciate very much. It's also my second time here. I work for a company called Work Microwave. We design and manufacture components for the ground segment. We've heard all about the immense changes in the space, digital payload, enormous throughput through the satellites, enormous flexibility. And in order to take advantages of that technology, you also need to adjust your infrastructure on ground. Yeah, so I'm going to talk about it and ways how you possibly might adjust your infrastructure to take advantage of these advances. So first, I will let you know what kind of equipment was used for this kind of study. Then we will talk about the challenges in Q and V band. Then I will describe the study itself, how it was conducted, and then we draw some conclusions from there. So we used, one of the goals of this study was actually not to go too deep into technology, not to customize too much, but instead using more off-the-shelf standard devices with less or non-customization. So we used a standard wideband IP modem AX80, which is capable up to 500 megasimples per second. I think Carl mentioned yesterday that would be a ship. Is that correct? Roughly? Yeah, the demand for a ship. So this is a very, I refer to this device as a software-defined radio with the hardware box. Yeah, so it's very flexible, very powerful solution. You need modulator, demodulator, and on the other hand, you need also converter, up converter, and down converter for up and down link. So we started in Q and V band very early. So we have a radar section which actually dealt with that topic before 2016, but the Satcom division started 2016 with two projects. So the first one was single channel synthesized local oscillator, up conversion from L to Q band. And the second was single channel from S to Q band. Then in 2017, we had another project, which was then conversion from L band all the way to V band. So 2017, we were able already to go up to 51.4 gigahertz. And in 2018, so last year, in order to get the advantage to cover the whole range in V band, you have to apply the multi-channel approach. So that's what we have done last year. So we implemented several channels to cover the range. So we could cover from 47.2 to 51.4 gigahertz. And in January this year, we started the serial production. So in January, the first units were shipped to the customer. Similar to Ka band, we had a discussion Ka band a couple of years back. Now we are going to, or approaching Q and V band. And similar to the time before, we face certain challenges. These are related to the operation as well as to the product itself. So most of the requests that we get cover 47.2 to 51.4, which is around 4 gigahertz, with the famous gap that we were discussing previously, yeah, the 200 megahertz gap. And the downlink is actually even larger. Typically, it's about 5 gigahertz. Yeah, so that's not easy to cover. From the perspective of the operator, the atmospheric attenuation is the hardest challenge, actually. Yeah, as much as we love oxygen and water, the first 10 to 20 kilometers in the atmosphere, they cause significant attenuation. We've seen that in Ka band, and we see that even more in V and Q band. So the numbers that I've seen was under clear sky conditions, 1 to 2 dB roughly attenuation, and in case of rain, it chops up to 10 dB and higher. Yeah, so you have to be aware of it, and you need a diversity side. Also, for the provider of this, of the converters, there are several challenges. So typically, the requirements are not really relaxed. Yeah? So they are similar to KA band, so the specifications are fairly tough, and you have to make effort to meet these specifications. As I previously mentioned, you have to cover in the up conversion typically 4 gigahertz, in the down conversion around 5 gigahertz, which is also not simple to realize. However, probably the biggest learning curve we went through was to set up proper measurement procedures. Yeah, so what you want to achieve is basically if you test a unit and you test the same unit tomorrow, you have to achieve the same results. However, the measuring equipment, the procedures which apply to C, KU band, KA band do not apply in the same way to V and Q band. Yeah, so that was really a tough task for us, and it takes time to make these experiences and to train your personnel accordingly. So from technical point of view, how is it realized? So the up conversion is realized in 2 stages. So typically we have multiple channels, each channel with its own local oscillator. So you convert from L band to an intermediate frequency, then you combine all these channels into one and do the final stage of the up conversion, then up to the transmitting frequency. So the intermediate frequency can be C band, can be KU band, does not matter basically to us. The RF performance or the specifications, they are similar. Here are some examples. They are similar to KA band. So it's I think, hard to see, but the blue line represents V band, the green line KA band. And you see they are very similar. So one chart is the phase noise, the other one is the gain flatness. You can also see this one is spurious, also well within specifications, and group delay. So now I described the wideband feasibility study itself, how it was conducted. So as I mentioned, the up conversion is done, or we do it, in 2 stages. And now what you can do is you can separate these 2 stages physically. So the first, let's say you get a larger box with for the conversion L to intermediate frequency, which can be indoor. Then you use an optical link, fiber optic cable, and connect it to a much smaller outdoor box, for example. Yeah, so that was the idea, how you can improve or add flexibility to the ground station equipment. So the motivation is, in the antenna hub itself, there is just limited space, and especially if you want to get close to the feed, and in these high frequencies, you need to get as close to the feed as possible. Then, you know, the space is the premium. So therefore, you need box which is as small as possible. Also, the transition or transmission of the intermediate frequency should be loss-free almost, or loss minimized. And it helps also it allows for easier integration in the hub then. So as I mentioned, there are some advantages. Basically, loss-free transmission of the intermediate frequency. The distance, because of the fiber optic cable, can be very large. So you can have the indoor equipment somewhere else, and of course the antenna can be far away. And because of the fiber optic cable, it's resistant against electromagnetic interference. On the other hand, there's a trade-off. So the downturns are basically some technical features of the optical transceiver with a little bit higher noise figure, and also it induces additional gain ripple to the system. So if you compare somehow the performance, so the conversion gain is the same, the noise figure with the optical cable is higher. The output noise density, roughly the same. And so is also the 1 dB compression point is on the similar range somehow. So how was it conducted? So we had indoor equipment which consisted of the modem, AX80, then the indoor up converter from L-band to the intermediate frequency, optical link to an outdoor box, transmission at 49.05 gigahertz, and on the receiving side you had a down conversion from V down to L-band and back to the modem. And we were, in that setup, we were able to demonstrate these 500 megasimples per second. Yeah, that's very much feasible. We had a similar demonstration at IBC. So eventually you've seen that at our booth this year, where we had just 2 off-the-shelf converters, 1 up, 1 down, modulator, demodulator. Yeah, and at 50 gigahertz, we were able to have a link. So the link is only between the horn antennas. So it's a little bit difficult to see. So basically each converter has a horn antenna. They point to each other. And the trickiest part was to align them. Yeah, because of these, you get reflections and so on and so on. So that was the tricky part. But otherwise, we could also have, we could realize a throughput of 3 gigabits per second. It was not an issue. Yeah, so many customers were impressed with that. So what is the conclusion? So we were able to demonstrate with basically off-the-shelf device, you know, the capability of high throughput with high flexibility on the ground. And we did not really optimize, let's say, also the optical cable or anything like that. It was just off the shelf. Yeah, so there's still a room for improvement. Thank you very much.